Okay, so let's go ahead and get started. Couple of quick administrative things. Hopefully by now you've turned in homework 1 already. I have to apologize for homework 2 not being out already. It's ready, but we need to figure out how to post it, given that I don't have a laptop. On Sunday, my laptop decided to go to Laptop Valhalla. So now it's in the laptop hospital, and hopefully by the end of the day I'll have a new one. But it's a little bit hard to do stuff from my iPad. So the TAs help put the homework together, and we'll post it as soon as we can. But because we're posting it late, we still want to give you sufficient time to work on it. So it'll be due not on Tuesday, but on Wednesday. And I say that with some fear, knowing that I have office hours on Wednesday morning. If you're coming to my Wednesday 10 o'clock office hours to try to figure out how the homework's going to do, let me warn you in advance, I'm not going to tell you the answers to the homework. I'm happy to, look over your own solutions and give you hints, but by 2 hours before the deadline, that's not the time to be looking at the homework for the first time, certainly. There's that. The other thing is, in order to record your homework 0 grades, it's helpful if you're already in Canvas as a registered student. It's a new system, so nobody really knows what's going on. Apparently, you can get into Canvas without the code by following the correct steps, which somebody has outlined on Piazza already. I don't know what the activation code is supposed to be for. It asked me to set one up, but as far as I can tell, no one's been able to. Has anyone been able to successfully use the activation code to get onto Canvas? Yeah, that's what I thought. Maybe it's necessary if you're not coming from an Illinois.edu email address or something. But supposedly, if you log in with your NetID and your normal NetID password and you follow the right path through the system, you're just in. It's not the end of the world. We'll still have other records of your grades, but it would be very helpful if everybody actually got in. And with Moodle, you would just automatically be in, but Canvas doesn't have that set up yet. Okay. Are there any other administrative questions before we go on to building things? Okay, so what I want to do today for the first chunk of the lecture is I want to go through some standard techniques for building DFAs. The most standard of which is brute force, but there's a couple of techniques for how one thinks about DFAs that may prove helpful when you're dealing with DFAs that you'll design in section tomorrow or on homework 2. So let me start just by reminding you of the actual definition. Now I'm going to write down the definition formally, but in almost all of the examples that we're going to do, because we're designing specific machines, the description that we'll give of the specific machine is a graph with nodes and arrows between them with labels. But I do want to remind you what the formal definition is, because that isn't always the easiest representation to use. Sometimes you really have to fall back to formality. So a finite state machine. Let me see if I can figure out how to turn that buzz down. Okay. Maybe not. Let's see, can you guys still hear me in the back? Okay. Hopefully that'll be better. So a finite state machine, this is also called a DFA. for deterministic finite state automaton. Deterministic means the behavior of the machine is determined by the transition function in the input. Consists of the following pieces. There's a finite set sigma called the alphabet. There's a set Q, which is also a finite set of the states. There's an element of Q called the start state. States are generally in this picture going to be represented in the pictorial version are going to be represented as nodes, little circles. The start state is going to be represented by a circle that has an arrow coming in from outer space. I have a subset of states, which are called the acceptor accepting states. Those will be represented by double circles. And then there's a transition function, which takes a state and a symbol in the alphabet as input and produces another state. This is the transition function. And generally that will be indicated by a labeled arrow in the picture. So if I start in state P and end in state Q, this picture is the same as saying that delta of P comma 1 is equal to Q. Okay, so when you ask to design a DFA, this is what we want. Now, generally, when we say build a DFA that accepts all strings with a certain property over the set, with the alphabet 0, 1, we've given you the alphabet, so you don't need to specify that. But you do need to specify the states, which one is the start state, which ones are the accepting state, and what the transition function looks like. And you can specify that, if you need to fall back to formality, you can just build a big table that has, one entry for every state, one row for every state, one column for every symbol, and you just fill in the table. You can describe it using a graph, something like 0, 1, 0, 1. Or you can possibly describe it using something that looks like math. Right, so this one down here on the bottom right, that's the transition function for our multiple of 5 DFA that we saw on Thursday. Okay. I don't care which of these various representations you use in the end, as long as your answer is clear. For things that tend to have, on the order of 5 to 10, maybe at most 10 states, chances are pretty good that this is the clearest picture. Just draw a picture of the DFA. Once you start getting into DFAs that have dozens or hundreds of states, you probably want to find some kind of structure in the transition function that you can describe as though the delta were an algorithm that you're implementing rather than an array that you're looking stuff up in. Okay. All right, so questions about the definitions before we start doing examples? All right, so let's build the DFA. I feel like I'm going to turn into the Incredible Hulk over here. This is sort of, I want to accept the set of all strings containing the substring 0, 0. Right? This is a language. I want to build a DFA that accepts precisely this language. Okay. Now I know that this language is regular because, at least if I'm working over a binary alphabet, here is the regular expression that describes it. Anything followed by a 0, 0 followed by anything. But now I want a DFA that accepts this. So before I suggest anything, let me ask you what I should do. What should I have as the states? What should the graph look like? Don't worry about making it simple. Don't worry about making it efficient. But tell me what you might imagine the states of the machine might be. Yeah. Okay, so I need a start state. Okay, so you're starting to build the graph as the DFA as a graph. Okay. So I'm going to have a start state. You come in from outer space. If you read a 1, it's like, I haven't learned anything. So you just keep reading 1s. That's okay. But now when I read a 0, okay. So I read a 0. I'm going to go to a new state. For lack of a better word, I'm going to call that state A. Now what? Okay. If I read a 1, I go back to start. If I read a 0, okay. Right. 1. Good. In other words, exactly this thing that I planted in your subconscious 5 minutes ago. Right. So did everybody follow what this DFA is supposed to be doing? Right. Now, when we're thinking about building the DFAs, one thing to keep in mind is what the states mean. Right? When we were building regular expressions, you kind of want to keep in mind, oh, this sub-expression stands for things with an odd number of whatevers, and this sub-expression stands for things with an even. When we're building context-free grammars, each non-terminal has a purpose. It's like this is the set of strings with more 1s than 0s, and this represents the set of strings with fewer 1s than 0s. So I should try to keep in mind what each of these states means. And so if I'm in state S, what does that actually mean? Maybe I can turn this down. Zoom out. Nope. I'm going to try switching to a different microphone while you guys think about this. B. What does that say about the string that I've read so far?
It definitely has at least one such.
Okay, so I've seen 0, 0. So what does it mean if I'm in either state A or state S? I have not seen 0, 0. But there's a difference between S and A. So one of the conditions that needs to hold in order to be in state S is I have not yet seen the substring 0, 0. And that's also a condition I need to be in state A, but that's not enough to tell me whether I should be in S or whether I should be in A. So, yeah.
A is if I read 1, 0.
No. So, for example, imagine I start at state S, and now I read a 0. I'm in state A. I have not seen a 1, 0. No. Yes?
0. If you've not seen 0, 0 in the last.
Okay, good. So state A is the last symbol is 0, and state S is the last symbol is not 0. And I'm writing this carefully. I don't mean to say that the last symbol is 1, because maybe I should write previous here instead of last. The last symbol I've read so far. Because when I'm starting out, at the very beginning, I'm in state S. But I haven't read anything at all. So in this case, the previous symbol is undefined, right? So I could write instead of is not 0, is 1 or undefined, just to be pedantic, okay? And this is an exhaustive breakdown of all possible cases. For any string, either that string contains a 0, 0, and reading that string would put me in state B, or that string doesn't contain a 0, 0, and it ends in a 0, in which case reading that string would put me in state A, or it doesn't contain a 0, 0, and it doesn't end with a 0, in which case I would reading that string would put me back in state S. Okay? Good. So when you're designing these machines, at some intuitive level, it's actually easier to draw the picture than to tease out what the picture means. But I really do want you to tease out what the picture means, because this is a sanity check to make sure that, yes, in fact, you're doing what you think you're doing. Right? It's quite easy to throw down 4 or 5 state machines and convince yourself that they're right when they're not, because you're not at least doing the minimum breakdown of cases and interpreting what each of the states means. Okay? Good. So let me try a slightly more complicated example. Strings containing the substring 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1. Okay, I'm not going to be able to draw this one. It's going to have too many states. Now, I know because I've been studying this stuff off and on for, more time than I care to admit. I know that, in fact, in this case, there is a DFA that accepts this language that has only 13 states. That's one more than the number of characters up there. But coming up with that from scratch, if you don't already know the trick, is near impossible. So I'm going to recommend that we don't try to come up with the trick. I'm going to recommend instead that we try very, very hard to be stupid and just go by brute force. So imagine, if you will, that you have a long string of tape filled with zeros and ones. And I'm going to feed you this tape one at a time, and I'm going to ask you, at any point on this tape, do you ever see 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, or whatever pattern of 12 strings I want, 12 symbols I want. In other words, if you're writing an algorithm that said for I equals 1 to n, do something, What do you do?
I want to think of this as a, as an algorithm. What do I put here?
You could have one place marker.
So I don't know what that means. I do know what that means, but you haven't actually said what it means, so I'm going to pretend that I don't know. What does it mean to be at a place in the substring? What is this I of which you speak, being in the substring? A state. So I could have another variable that, so I'm going to keep an index j into the pattern. Okay. Then what? Right. So if the symbol that j points to in the pattern is equal to the symbol that I points to in the text, great. I have a match. I move forward. What if they're not? I'm sorry? I don't want high-level details. I don't want intuition. I want you to give me code. Okay, so I just start J over. Doesn't that possibly miss some other matches where, maybe it doesn't, its character I in the text doesn't match this 0, but maybe it matches this 1 that isn't at the beginning of the string? You're trying to be clever. Stop being clever and tell me how to do it. Be stupid, brute force, slow, how do you do it?
For j equals 1 to 12, check if the pattern at position j is equal to one of the last 12 characters.
In other words, at every position in the text, look at the last 12 characters and check, is it equal to the pattern? No cleverness involved. You just, is it here? Yeah, no. Is it here? No. Is it here? Yes. Ding. The light bulb goes off. Okay?
Compare the last 12 symbols to the pattern.
Just, right? I could do this in a for loop. And if they're equal, then I set a flag to be true. Right?
If they're equal, then I'm going to set some flag to be true, and I'll initialize that flag to be false. And at the end of the day, I'm going to return, that flag, true or false. Okay? There is a clever solution that involves keeping one finger on the text and one finger on the pattern. And when there's a mismatch, moving the finger on the pattern backwards. But getting that right is incredibly subtle. There's an algorithm called string matching algorithm by Knuth, Morris, and Pratt. It's 8 lines long. It is by far the hardest 8 lines of code I have ever read. It is really hard to understand what's going on, which is why I want to avoid it for now. Okay. Now, how many different states can this algorithm be in at any given, for any particular value of I? And to answer that question, I'm going to look, what are the variables? What are the things that I would have to remember? One of the things I would have to remember is I'm only going to see one symbol at a time, so if I want to reason about the last 12 symbols, I have to remember the last 12 symbols. And a new symbol will come out, and an old symbol will the 12th oldest symbol, the 12th youngest symbol will leave, and then I have 12 new symbols, right? So I'm going to have a variable that stores the last 12 symbols that I've read. I also have a variable, yes or no, this flag, that decides whether or not I've actually seen the pattern. Okay? How many different states can those two variables be in collectively? And let's imagine that the symbols are all zeros and ones. So this can be in, this has two possible values. How many possible values does the variable last 12 symbols have? There's a slight problem with 2 to the 12. 2 to the 12 is close. The problem is, what do I store in that variable when I'm reading the 6th symbol in the input? Right, so in fact, you also have to, this is 2 to the 13 minus 1. You also have to keep track of possibly fewer than 12 symbols when you're at the very beginning of the string. Okay? So roughly this means I'm describing a DFA with about 2 to the 14 states. Okay? The state is 1 bit for have I seen the pattern, and another 12 or fewer bits for what are the last at most 12 symbols that I've read. Now, I could now, at this point, if I really wanted to, I could write code that takes in one of these states as input and takes in a single symbol and produces a new state in this form as output. And that would be a description of a DFA. 2 to the 14 is about what? 16,384. Right, so this is a DFA with 16,000 states. Don't draw it. Okay? If your goal is to prove that a language is regular, we're done. I have described, with some missing details, but I basically described a finite state machine. Finite is very big, but I don't care. Right? And one of the reasons why, and I'll mention why I don't care, and I'll mention this again later in the lecture, there is an algorithm that can take in a DFA and produce the equivalent DFA that has the minimum number of states. So there is an algorithm that can take in this 16,000 state DFA, grind away for a while, and spit out the DFA that has only 13 states. So why should I waste my neurons coming up with the DFA with only 13 states? That's why we have machines to do things like that for us. So in general, I'm not going to be terribly concerned about minimizing the number of states. If the goal is just to prove that a DFA exists, this is a fine existence proof. On the other hand, if the goal is to actually pull out some interesting structure, or you want to draw the machine, it's often useful to do a little bit of thinking to keep the number of states down so that the answer is clear. But I would accept this as at least a skeleton of an answer. If you said, prove that a language is regular. Okay. Any questions? Okay, let's come back down to earth. Let me do something simpler. So I want a DFA that accepts all strings that contain a 0, 0, and then later contain a 1, 1. Right, we already know how to find things that contain 0, 0. Any idea how we might perhaps, there's an easy modification that gives us a DFA that finds strings that contain the substring 1, 1. Is there some way that we can take the 0, 0 DFA and the 1, 1 DFA and put them together and get a DFA for this? Any ideas? Yeah. Okay, so I want you to stop me when it look like I'm about to draw something that doesn't belong. Now, should I draw a loop here? Okay. What? Okay, draw a loop here, labeled 0. Okay, 1 needs to go somewhere. What should we call that? I'm sorry?
0, 0, 1.
Oh, good. Well, just call it 0, 0, 1. In fact, I'm going to call this one 0, 0, and I'm going to call this one the 0 as a mnemonic for what the state actually means. So here, the last symbol is a 0, but I haven't seen 2 yet. Here, I've seen 2 zeros. Here, I've seen 2 zeros, and the last symbol is a 1. Which means here, I've seen 2 zeros and the last symbol isn't a 1. Where do I go from here? Backwards if I see a 0. Forwards if I see a 1. To this new state, which I should call what? As a mnemonic, what should I call it? Yeah, I've seen a 0, 0, and I've seen a 1, 1. And this is an accept state. And now anything I like. Okay? So you'll notice this is really just the 0, 0 machine glued on, in some sense, to the 1, 1 machine. All right. Now, one thing that we know about regular languages, and I told you that the languages that are accepted by DFAs, they're regular. One thing that I know is if A is regular and B is regular, then the concatenation of A dot B is regular. Right? Because I write down the regular expression for A, and I write down the regular expression for B, and I just glue them together, and that gives me the regular expression for A dot B. You might think that you could do something similar with DFAs, and you'd be wrong. Right? This is fine as a mechanism for this particular kind of problem, where you want to know, does it contain substring W, and then later, does it contain substring X? As soon as you find the W for the first time, you can just start looking for the X. In general, you can't glue DFAs like this. Okay? So there's a bit of a danger in showing you this. So I'll just, I'll write here, danger, not with the internet spelling, but with the actual E here. If, for example, I say, build a DFA that accepts all strings in this that are composed of a string in language A and a string in language B, don't just build a DFA for A and a DFA for B and try to glue them together. In particular, because the DFA for A might have more than one accept state. And you can't sort of glue it onto the single. But for contains this and then contains that, this is fine. Okay. All right, let me try a slightly different one. No 1, 1 after 0, 0. Okay, I want strings where I might have 1-1s and I might have 0-0s as substrings, but I will never see a 1-1 after a 0-0. And there's a reason why I haven't pulled the other machine off the screen. Yeah.
So just make the 0011 not a second string?
Right, so the language that I've described at the top of the screen, there's no 0-0 after a 1-1, is the complement of the language that I've just finished dealing with. Okay? In other words, it's the complement of strings containing 0-0 and then 1-1, right? If a string is blah, 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 0-0, blah, 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 1-1, blah, 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 it's in the second language. Otherwise, it's in the first. Okay? So I'm trying to build the DFA for the complement of the language where I already have a DFA. In other words, I want to accept precisely when the other DFA rejects, and I want to reject precisely when the other DFA accepts. And so the way that I build this language is, this DFA, is I copy exactly the states and the transitions and the start state. And then I say, oops, this should be a reject state, and these should be accept states. Okay, the only difference between these two machines is that set A. Which states trigger an acceptance versus which states trigger a rejection. Okay? So one of the things that this idea implies is if A is regular, then the complement of A is also regular. Now this statement, the complement of a regular language is also regular. The proof is one line. You build a DFA for A, and then you flip which states accept and which states reject, and that gives you a DFA for the complement of A. Okay? So provided that you understand that regular in this, for this theorem, means accepted by DFA, as opposed to in this theorem, where it means described by a regular language. Now, again, this is one of the, these are both true properties of regular languages. Both of those definitions are identical, although we haven't seen a proof yet. But what it shows is that sometimes when you're reasoning about regular languages, for example, when you want to think about concatenation, it's easier to think about them as things described by regular expressions. And sometimes, for example, if you want to think about their complements, it's easier to think about them as languages accepted by a DFA. It's really not straightforward to take a regular language, a regular expression, and transform it into a regular expression for the complement. You can do it, it's possible. It usually involves some sort of exponential blow-up. You really don't want to. It's much easier to say, here's a DFA, look, I can flip the states. Okay? So questions about complement? Okay, good. So let me do one more. Okay. Okay, so previously we looked at things that contain a 0, 0, and then later contain a 1, 1. I want to look at a larger set of strings. The condition now is somewhere in the string there's a 0, 0, and somewhere in the string there's a 1, 1. Now, I know how to build a DFA to detect the first condition, contains a 0, 0. You know, I can just draw that DFA again. Okay. Right, this is the machine that detects whether the string contains 2 zeros in a row. And I know how to build, I know how to construct a machine that decides whether a string contains 2 ones in a row. And in fact, it's really the same machine, just with the arrows labeled the opposite way. And somehow what I want to do is I want to run both machines at the same time. Imagine I want to put my left finger on the 0 machine and the right finger on the 0, 0 machine, and my right finger on the 1, 1 machine, and I want to trace them both. And at the end of the string, if my left finger is on the accept state for machine A and my right finger is on the accept state for machine B, then I'll say yes, and otherwise I'll say no. Okay? So I'm going to do exactly that. My body is the DFA. It's in a finite number of states. How many states can it be in, given that the only thing I'm going to move are my fingers? How many states can my fingers be in? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 2 variables, R and L. R is either equal to S, to A, or to B. L is either equal to S prime or A prime or B prime. So altogether, my fingers can be in are always in one of 9 possible states. Okay? So the actual machine that I build is the product of these 2 machines. It has 9 states. And when I'm, say, in this state here, second row, third column, what that means is that the 1 machine is in its second state and the 0 machine is in its third state. Okay. If I think of a DFA as an algorithm that has some variables in it, right, that DFA at the top is an algorithm that has 1 variable that has 3 possible values, and that DFA on the left is an algorithm that has 1 variable that has 3 possible values. If I just put the bodies of those for loops together into a common loop, I now have a for loop with 2 variables, each of which can have 3 values. So internally I can be in one of 9 states. Now, if I'm in this state and I read I suppose I should, yeah, and I read a 0, my right hand stays put and my left hand goes up, which means my global state goes from second row, third column to first row, third column. 0 goes like this. Okay? So that allows me to describe now explicitly what the transition function is. So let me start by putting in all the zeros. So notice if I'm in row 1, my left finger is never going to leave the start state. My right finger is going to move, though. So if I'm in column 1, I'm going to move to column 2. If I'm in column 2, I'm going to move to column 3. If I'm in column 3, I'm going to stay put. If I'm in row 2, and I see a 0, I'm going to move to row 1. And then my column is going to change just as it did in row 1. So if I read a 0 from the state on the middle left, I'm going to go to the state in the middle top row. Likewise here, I'm going to go to 0. And finally here, I'm going to get a 0. Finally, if I'm in the last row, again, if I read a 0, I don't change the rows. So again, I'm going to get the transitions that look like this. Similarly, now I can fill in the 1s. Again, I'll do this row by row. If I'm in the top row and I see a 1, that's going to push me down to the second row. Here, I don't change columns. Here, I do change columns. Here, I don't change columns. In the second row, if I read a 1, I'm going to go down to the third. So it's just going to look a lot like what I just did. And finally, in the last row, if I read a 1, I'm going to stay in the last row. So which column depends on the machine on the top. Okay? That's the transition function. The start state is the two component machines start at, well, the vertical machine starts at the top row, and the horizontal machine starts at the leftmost column. So my start state for the product is the combined state in the upper left corner. And finally, I want to accept a string if and only if, when the string ends, each of the component machines, both of the component machines, are in an accept state. And there's only one global state that allows me to do that, and that's the one down here in the lower right. Okay? So this 9-state machine accepts all binary strings that both contain the substring 0, 0 and contain the substring 1, 1. Right, now, an interesting feature of this machine. Yeah, sorry, question.
State in the middle that nothing goes into.
Yeah, there's a state in the middle that nothing goes into. What's up with that? I don't care. Remember, I told you there's an algorithm that can take in a state machine and spit out a minimal state machine. And what that algorithm will do in this particular case is it will say, hey, that state in the middle, you don't need it. You can get rid of it because you can't get to it. So this state in the middle is redundant, right? So I can just throw it out. And then it turns out that the rest of the machine is actually minimal in this particular case. I mean, this won't always be so simple. Okay. So this product construction can sometimes give you things that are more verbose than necessary. They may have unnecessary states. They may have states that can be merged. They may have other states that can just be thrown away because they're not reachable. That's fine, right? What this does give you is a recipe for computing, describing a machine that accepts the intersection of two languages where you already have machines. Right? So I'm going to go through the general mechanics of doing this, which is going to involve writing down a bunch of symbols. But the picture that I want you to keep in your head is this one right here. And the state of the machine in the middle, which seems to only have, I could use with one finger, is the state of my two fingers, where I have one finger in one machine and one finger in the other. Okay? So how do I do this in general? I'll come back to the example after I walk through the definitions here. Okay, so the full-fledged product construction. Okay, so suppose I'm given two DFAs. So I have M, which has an alphabet, a state set, a start state, a set of accepting states and transition function, and another one, M prime, which has the same alphabet and a different start state, a different set of states, different set of accepting states, different transition function. Okay? And where M accepts some language L, and M prime accepts some language L prime. Okay? So I've built, I have a language L, I built a DFA for it. I have a language L prime, I built another DFA for it. Okay? Then M double prime, which I'll define below, accepts the intersection of these two languages. Okay, so Q double prime is, well, a state in the product machine consists of a state in the left component and a state in the right component. Right, so this is the set of all pairs, little q prime, where little q comes from the first machine and little q prime comes from the second machine. Or in simpler terms, q cross q prime. Okay, it's the product of these two sets, meaning the set of all ordered pairs, where in each pair the first element comes from the first set and the second element comes from the second set. We've seen Cartesian products before when we were defining, this state transition table. So here it was state cross symbol. You get this nice little two-dimensional array. Here it's state cross state, and you get this nice two-dimensional array. The start state for the product machine is, well, each of the component machines is in their own individual start state. Okay? The accepting states for the product machine are all pairs QQ prime, where Q is an accepting state from the machine 1, and Q prime is an accepting state for machine 2. In other words, A cross A prime. Okay? The accept state is all pairs where the row is one of the accept states in the vertical machine, and the column is one of the accept states in the horizontal machine. And then finally, I need a transition function. And the signature for the transition function is state cross symbol to state. But remember, a state is now actually a pair cross symbol to state. That's a pair. It's defined as follows. So the state that I go to, if I start in QQ prime and I read symbol A, is defined to be an ordered pair. Anyone care to guess what goes into the two pieces of that ordered pair? I know you know, because you seem to know everything. Yes, you're right. I can read your mind from here. Let somebody else answer. So remember what the states mean. The first component of that pair is, where is my left finger? The second component of the pair is, where is my right finger? So if my left finger is at Q and my right finger is at Q prime, and I read the symbol A, where does my left finger go? Yes? Yeah? Right. I let the first machine tell me where to move my left finger. And then what goes in the other half? Everything prime. So I let the left machine tell me where to move. Well, I guess this is left and this is right. So I'm going to tell a recursive story. When I was a kid, I had a really hard time telling my right hand from my left hand, to the point where occasionally I could just swear blind that this was my right hand. Now, I've told that story when I was a kid, but when I told the story, I said, and sometimes I could just swear blind that this is my right hand, at which point the person listening to the story says, "It is your right hand." And I said, "See?" Now, I told that story like this, and I've told that story like this. I don't think I've recursed more than 4 levels deep. Usually at that point, people's eyes glaze over and they say, okay, we get it, Jeff, you're dyslexic. And also a bit of a geek. Okay, so this is the sort of formal product construction for how you get a DFA for the intersection of 2 languages if you start out with a DFA for each of those languages individually. And this is precisely the recipe that we applied here to get strings that contain a 00 and contain a 11. I started with the 00 machine and the 11 machine, and I just blindly, mechanically followed that construction. Okay, so that just to make sure that we're on the same page, what if I wanted to change this from an and to an or? What would I need to do differently?
Well, I think part of the or would
Huh? Sort of the union, but let's be concrete here. This particular construction, for this particular machine, I claim that I still need I can still do it with 9 states and this transition function, but
You can add acceptance state on the bottom line and the right line.
right. So now a state in the middle machine is accepting if either the state on the left corresponding to that row is accepting, or the state on at the top corresponding to that column is accepting. So all I did was change an and to an or in the definition of the language means I change an and to an or in the definition of which states are accepting. And that's it. So if I wanted to change this to union, I change this to an or, and this is no longer true. And that's it. It's the only change. And in general, I can take any way of combining 2 different languages together into a new language. I can define any conditions from language 1, any conditions from language 2, combine them into a new condition for language 3. I can build a DFA for language 3 out of the DFAs for the first 2 languages by just doing this product construction and figuring out what the exact condition is that I need to apply to the accept states. Okay? I could say it's in this set but not in that set, for example, would be something that I could reasonably do. Okay. Now, one of the consequences of this product construction is that we now know that if A and B are regular, then A union B and A intersect B are also regular, right? Now, the union, this is sort of easy with regular expressions. Right? If I have the regular expression for A and I have the regular expression for B, I can get a regular expression for A union B by just putting them together with a plus. Maybe some parentheses to disambiguate. This is really, intersection is really hard to do with regular expressions. I know that a regular expression for A intersect B exists if A and B has one. But in general, it's going to be pretty ugly and complicated. And I don't know of a really good systematic way of constructing it. Whereas both of these are relatively easy for DFAs once you sort of internalize what this means. Okay. So we've seen a couple of other closure properties. You know, A dot B is regular. Sigma star minus A is regular. It's not too hard to see that, for example, that A star is regular. And there are a couple of other rules like this where if you can describe a language in terms of simpler languages, and you know the simpler languages are regular, then you know the more complicated language is also regular. Now, some of this, like A union B and A dot B, this is essentially the definition of regular. And others, like A intersect B and sigma star minus A, these are not really part of the definition. These are things that you derive by looking at through the lens of DFAs. But you may find yourself at some point being asked, prove that the following language is regular. And the answer might very well be, this is the intersection of three languages that we saw in class, QED. Because I know that the intersection of regular languages is regular, and Jeff proved that these three languages are regular in class. So this is a fairly useful tool to have in your tool bag. Okay. So this is as far as I want to go in terms of techniques for constructing DFAs. Are there any questions before I sketch? I'm going to give you some definitions, but I'm not going to go through some. I'm going to give you an example, and I'll go through the details on Thursday, given the time. I need to say something, but it'll just be to warm you up. Are there any questions about how this product construction works? If I were to ask you, how would you describe a DFA that accepts the intersection of three regular languages, would you know what to do? Make a cube. Make a three-way product. Or you could say, okay, I build a machine for A union B, and then I build a machine for that union C. So I apply the product construction twice. Or you could just build a three-way product. It's the same thing. Okay? Good. All right, so the last thing I want to talk about start talking about now is which is not regular. Right, so we have seen lots of examples of regular languages. We now have two techniques for proving that a language is regular. You can build a regular expression, or you can build a DFA. I guess three, you can argue it's the intersection of three things you've already seen, or it's the complement of something you've already seen. But none of these can help you prove that something isn't regular. Okay? And it is actually possible to prove that certain languages can't be regular. I mean, we know from there's a cardinality argument that implies that there are too many languages compared to how many regular expressions there are. So you know, almost all languages are not regular. But that doesn't really help us much if we're given a particular language. All right, so I'm going to start by defining an equivalence relation. Okay? So I'm going to pick my favorite language, L, which might be regular and it might not. And now I'm going to define X to be equivalent to Y means for every string Z in my alphabet, XZ belongs to my language if and only if YZ belongs to my language. Okay? Now, this is a pretty abstract, bizarre-looking thing. So it might be good for me to sort of give you an example. So my running example for L is going to be the set of strings that start with some number of zeros and end with that same number of ones. Okay, 0 to the n, 1 to the n. This is one of the languages that you hopefully know how to build context-free grammar for. S goes to 0, S1, or epsilon. It's sort of a canonical, easy, context-free example. It turns out not to be regular. Okay? Let's claim, for example, that these two strings are equivalent with respect to this language. And the reason is that by saying, well, let's suppose I look at some string that I get by adding, I take some suffix z and I glue it onto 0, 1. Under what circumstances can 0, 1, z be an element of that language? Z has to be the empty string, right? The only way that this can happen is if z is equal to the empty string. If z has a 0, then I've got a 1 followed by a 0, and it can't be part of the string. If z starts with a 1, then I've got too many 1s. Okay? On the other hand, if I say 0, 0, 1, 1, z, when is that in the language? Again, if and only if z is the empty string, right? If z starts with a 0, then I've got a 0 after a 1, and so it's not even close to the right thing. If z starts with a 1, then I've got too many 1s. Okay? So those two strings, in this case, they both happen to be in L, but this is a relation on all strings, not just the ones in L. In this case, those two strings are equivalent. Okay, so let me give you perhaps a simpler example. The two strings are 0, a string of length 1, and 1. Are these two strings equivalent or not with respect to this language? All right, so I'm going to set x to be that, and y to be that. So is it the case that no matter what suffix I put onto these two strings, I will always get either two strings that are in this language or two strings that are not? Or the other possibility, is it possible to find a suffix z such that 0z is in the language and 1z is not? Okay, so suppose I take z equals 1. Then xz is 0, 1, which is in the language. The number of zeros is 1, and the number of 1s is the same. Right? On the other hand, yz is equal to 1, 1, which is not in this language. Okay? So 0 and 1 are not equivalent with respect to this language. Okay? Now, why do I care about something bizarre like equivalence? Okay. The idea is, let's suppose for the moment that I have a DFA for L. Okay. Suppose we have a DFA for L, and let's suppose further that I have two strings with the property that they both lead my machine, my DFA, to the same state. We'll say call it Q. So if I start in state X, if I start at the start state S and I read string X, I end up at state Q. If I start at state S and I read string Y, I end up at state Q. Right? Now notice, whatever I read after X and after Y, I'm going to follow exactly the same thing, right? Then for any string Z in sigma star, well, if I follow XZ, this is exactly the same as if I started at Q and I read Z. This is also what I get if I start at the start state and I read YZ. Okay? Once I'm reading these two strings X and Y and I converge to the same state. And now I start reading the same characters, I'm going to follow the same path because it's a deterministic finite state machine. The path is determined by the state that I start in and the characters that I read. Now, if this is an accept state, then XZ and YZ are in L. Otherwise, XZ and YZ are not in L. So in other words, the two strings are equivalent. Okay? If, for any DFA you like, if you read these two strings and that sends you to the same state in the DFA, those two strings must be equivalent. Now it's possible that X and Y could be equivalent for other reasons, right? But at least this is a sufficient condition for equivalence. You take any DFA you want, if you read these two strings and you end up at the same state, those two strings that you read must be equivalent. So what's the contrapositive of this? If X is not equal to Y, if they're not congruent, then I must end up at two different states. In other words, if I can find two strings that are equivalent, then among other things I have learned, if they're the two strings that are not equivalent, among other things I've learned that any DFA for that language has to have at least two states. The one that I get to from reading X, and the one I get to by reading Y. So if I could find three strings where X and Y are not equivalent, and Y and Z are not equivalent, and Z and X are not equivalent, three strings that all lead to three different states, then my DFA has to have at least three states. If I could find 10 strings where each of the 55 pairs is not equivalent, that means any DFA that accepts this language must have at least 10 states. If I can find an infinite set of strings such that every pair is not equivalent, then any DFA that accepts this language must have an infinite number of states. But how can you have a DFA with an infinite number of states? That's just silly. That's how you prove that a language is not regular. It doesn't have a DFA. And so I will leave you with the following set of strings. I will claim for this language, 0 to the n, 1 to the n, no pair is equivalent. And therefore, any DFA that would accept it would have to have an infinite number of strings. So this implies 0 to the n, 1 to the n is not regular. We'll pick this up again on Thursday. All right, thank you.